Good morning, everybody. Welcome to my talk about architectures for Linux and railway safety applications. My name is Florian Wühr. I'm affiliated with Red Hat. Unfortunately, Daniel couldn't be here today, so I will be the one taking over this talk. What we will discuss today are the following points. Short introduction about ourselves, Red Hat's role in the rail industry, safety applications in trackside and rolling stock appliances, certification hurdles, notable safety architectures for modern railway appliances, and then at the end, some conclusion questions. Who we are. So this is myself. I'm a senior embedded software engineer affiliated with Red Hat. I was working for Deutsche Bahn actually for 5 years in the area of safety relevant communication technology. I have now more than 6 years of experience in embedded Linux and 1.5 years experience in functional safety. And I'm currently working on a project for autonomous trains in Germany, which is a funded research project called Automated Train. In regards to Daniel, he was a university professor in Brazil for 30 years, worked at a automotive infotainment company for 4 years before he joined Red Hat, at pretty much the same point as I did, and we are both working on the project Automated Train. So let's jump into it. What Red Hat's role is in the rail industry. If you might be thinking, what does Red Hat have to do with anything in railways? And it's not clear from the start, so let's give it a short overview. Currently, Red Hat products are not actively used in railway functional safety applications. That's what I have to say up front. We want to get into this market. It might be interesting also to use other open source projects or other open source based products from maybe other vendors. But right now, this is somehow a post oligopoly market. We are now actively participating in this governmental funded research project, Automated Train, researching grade of automation for automated train operation. So for those of you who are not familiar with the automation grades, grade of automation 4 is the equivalent to level 5 autonomous driving as in automotive. So there is no supervision or anything needed. This is really fully autonomous operation. What is Red Hat's role in this project? So we want to investigate a manufacturer-independent high-performance computing platform for autonomous driving. This isn't necessarily being limited to railways, but it's of course under the railway umbrella. And we want to investigate the transferability of Red Hat's automotive safety solution, the Red Hat in-vehicle operating system. I'm sure many of you are familiar with it, into the railway domain. So if you have any questions, feel free to raise them at any time. It shouldn't be... Yeah, please go ahead.
Are there any really open source projects related to railway? Like open railway, whatever.
So there are some. This market is at the moment opening, I would say, because some jurisdictions like Switzerland, for example, they introduced a new law where they have a pretty simple principle, which is public money, public code. So if there is anything developed in a publicly funded project, the results need to be open source anyway, by law in Switzerland. And this is where it takes up to speed, since Switzerland is a pretty good example of how railways are supposed to be working. Many of other countries try to copy it, and there are some initiatives like the Open Rail Association, for example, where a lot of companies, especially in Europe, are trying to do joint architectures the open source way, I would have to say. But and there are also some open source projects, like for example, the Rasta stack that is being used. But this is also something that was developed by in Switzerland with public money, and I think other countries don't have these restrictions by law right now. But I personally think it's a good idea. Did this answer your question?
Yeah.
Perfect. So back to my slides. Just a short overview of what automated train does. I have stolen these slides basically from a presentation that the automated train project gave publicly anyway. So I guess there's nothing wrong with showing them here as well. What the automated train project wants to demonstrate a fully automated preparation and parking of a railway of a railway vehicle. So you can imagine if a train is not in operation, it's being placed on some kind of side track. And at some point, if you want to put it back into operation, somebody currently needs to get onto the train, gets it up and running, and needs to drive it to the platform so that passengers can get on it. And this should be done fully automated at the end, so that a train driver who takes over the actual driving on the track can only board the train, but also has a fully operational train available when he starts. So that's the idea. There you have some parts of it. So basically, the important parts of data factory, the environment detection on the platform. We as Red Hat are in the part of the project where we research the safe onboard high performance compute platform, which of course has some parts of the software stack, as I show here, but I don't want to get too much into it. And we have a few partners whom we are working in this project. So it's Deutsche Bahn, also Siemens Mobility, Duagon, which is a company that provides railway grade hardware, Bosch Engineering, and Woodwork, with whom we are working together on the project. And if you have any specific projects about the project, questions about the projects, feel free to reach out.
It's all on your Linux at this point in time, or is there other RTOSes there incorporated?
We try to keep the requirements and the specifications as open as possible. Of course, since we as a Red Hat are part of the project, we of course want to research Linux at foremost, which should be used in this operation. But it could technically also be done with some other RTOSes or something like that. But especially if the high performance use case with maybe also GPU accelerations or something like that comes into place, the
Sort of thinking on the sensor side,
Yeah.
is there a multi-processor,
Exactly. If there is the need for more computing resources, the classical RTOSes come to some limits, I would have to say, especially in driver support for hardware or accelerators that are powerful enough to power these applications. And that's where basically Linux is the only logical choice.
May I ask you,
Sure.
can you list a few advantages that you see on autonomous train? Because for automotive domain, it's quite clear when you have also reason for driving going that direction, but for a train, it can be more difficult to understand.
Sure.
Yeah.
So, of course, this is a question at the end that society needs to answer, but we still have the situation, at least in Germany, that we have
This meeting is being recorded.
Whatever. So let's get back to your question. at least in Germany, we have the situation that we have a shortage of train drivers. Train driving is actually something that people are not so fond of, I would have to say. And it's difficult to find people. A lot of them are,
And then they go on strike all the time too.
that's the next thing. As Isaac mentioned, you have the situation since it's not like in the 60s or the 70s where these people used to be state or employees without the right of having to strike. They are now just employees of a private company, basically, and they of course have the right to strike for their rights as they see fit. And at the end, this leads to the fact that sometimes over months there are no trains in operation, and this is why we are really thinking about if it would be a good idea for autonomous trains. At some point for example, in Nuremberg, the U-Bahn is already also autonomously operated. So some lines are already autonomously operated. This is something that you see frequently throughout the world, that new projects are always being planned autonomously. Also in Vancouver, the SkyTrain, for example, is operated fully automatically, as I know. And this is
At airports too, the train between terminals.
exactly that's a trend that is getting up to speed. And to be honest, the technology that we have today is on the trains is already so much automation that the train driver doesn't have to do much anyway today. It's mostly about responsibility at the end. And of course, there are some difficulties getting it up and running. This is why there is a research project, but I guess there is a demand for it. If I don't say too much, Deutsche Bahn has decided to currently discontinue their efforts on automated train operation after this project has ended, and shift more to remote train operation, which is, I guess, a step backwards, but a step before. So each fully automated train solution at the end needs to have a remote train operation solution as a fallback anyway. So one leads to another, I would say, basically. But I will get to that maybe a little. So to give you a short introduction about potential safety applications.
Another question, which are the chosen safety standards and levels for this due to IC 61508 or in 5716, or what did you choose there?
So there is no worldwide standard for railways. It's mostly European driven. So most of the innovation in railways is historically driven from Europe. And this is why the European standards are elite, I would say. There are railway-specific standards for safety, which is EN 5129, EN 5716, which is the most recent that has been released. They are derivatives of IEC 61508, so there is this connection, of course. They use the same SIL levels as IEC 61508, for example. It has some specific stuff, like the railway standards, for example, know something like, I would say something like SIL 0, some integrity level that is below SIL 1. It's also called basic integrity. This is something that the railway standards have uniquely, I would say, and it's significantly easier to prove that you have this basic integrity in regards to any other higher SIL level. But let's look into it a little. What we currently have in operation in railways, since I guess most of you have an automotive background and are not yet so much in touch with railways and are just mostly customers, I would say. So this is an example picture for the European train control system, which is the de facto standard worldwide, I would say, for train controlling. You see the track, you see the signals, you see the balises that are reporting the position and the signal states, and you have the trackside signal control and track release reporting. And then, of course, you have the railway vehicle, which has the EDCS computer in it that is capable of scanning the Euro balise. This is done via induction technology. And they also use GSM-R as communication technology at the moment. There are plans to move to LTE and future standards like 5G or something like that. But as far as I know, this is currently not being done. So what you can say is railways is behind the other sectors, I would say at least 10 or 15 years at some point. So GSM is still the hot technology up until today on how what they use to talk to each other. And to give you an overview about the components and their safety integrity levels. So if you research a little bit, of course, that there is no company is advertising this SIL levels that they need to achieve. So it's kind of difficult to get some information if you don't have the risk analysis available from the companies. But at some point you find it somewhere in the literature, and you can, for example, say that the antenna needs to be SIL 2. Also, the computer in the train needs to be SIL 2 that is connected to the Euro balise. And for example, the signal and the signal control need to achieve SIL 4 because if there's going something wrong, catastrophic incidents might happen. So this is why there is the need for the highest safety integrity level. Another example, for example, in train, this is something that has been in place for quite some long time. It's called the Sicherheitsfahrschaltung. This is something like a deadman switch. You see this pedal down there. This is something that the train driver has to operate over and over again to signal the system he's still conscious and alive. And if he doesn't, at some point, the train will automatically brake. Because in railways, it's pretty simple to achieve the safe state. The safe state is always nothing is in operation. So everything is standing. This is usually the safe state. And this also has a SIL 2 integrity level. That needs to be
in cabin camera.
Sorry?
Do they have an cabin camera for the driver? I mean, I can put a brake on this.
To watch him.
To operate. No,
It's not brake. You need to push.
Yeah.
Whatever. But if like driver, in caution or something like that, do they have?
No. They have to press and release.
Press and
I
release.
understand. But what happens? Like, now in automotive, there are a lot of in-cabin camera just for the driver observation. I'm just wondering whether they have also in-cabin camera as well.
So I guess they don't. I guess due to data privacy reasons, that this should not be allowed. But I also don't see the need from safety reasons because you have this pedal switch.
I mean, depending on the operation, if you are on ICE train,
anyway, the driver is just there, right? If you're running up to 300 kilometers per hour, then even if you see something, you're already over it.
Yes, and if you're in such high-speed operations, you need to have the possibility from the infrastructure side to have a so-called continuous possibility to influence the train. This is what is possible with ETCS, as shown possible. So the infrastructure basically gives you a target speed at the train, and the train driver just pushes forward the acceleration pad. And if the target speed goes to 0, and the train driver doesn't pull the acceleration pad back, the signaling system will break the train automatically anyway. So this is something that is demanded by law. If you want to reach speeds higher than 160 kilometers per hour, which is the case for ICE trains, for example, you need to have the possibility at any point to get the train to stop. All right, so a future appliance for the automated train operation, for example. This is a demonstrated that Siemens Mobility has shown at some trade fair. So this is not in operation yet, but you would also have to achieve SIL 2 here for this. And I guess this gives you a pretty good idea of which SIL levels we are talking about, of the complexity of the systems. And if there are any questions, feel free to ask. Certification hurdles. What is a little difficulty in railways is we have a historic development, and the historic development wasn't unanimous in Europe and on the world. So we have different historic empires, jurisdictions, and they have made their own rules. I would like to have to say some examples is the track width, basically. We have the 1,435 millimeters, which is considered to be the standard gauge. This is what most of the countries use today, but not even within Europe. We have one track width. So if you go to the Iberic countries like Spain or Portugal, for example, they have a bigger one. So if you want to have a train that operates from France and goes to Spain, for example, it will eventually lead to a problem, because in France you have 1,435 millimeters, and in Spain it's different. They tried to change it, but of course you can imagine this takes time, and this is not something you do from one day to another. If you go to the east, for example, to Russia and everything that is being connected to the old Soviet Union, you have some other track with 1,520 millimeters. So if you see there is a world map with a different track width, you see there is every jurisdiction did it differently. That's one thing.
And I guess isn't it that even the track width in Europe goes back to the Roman times?
That might be the
It's
case.
going back because the Roman roads were made in a certain width, so that the horses and the chariots afterwards fit in there. And this even I heard this was the example of why certain rockets in US for space have a maximum size, because this is space as they need to go through tunnels, and they are transported by railways from one location to the other, and therefore at the end the Roman carriers determine the size of the rocket, booster rocket from NASA, space flights and whatever. So I think that's what they told me in the space, the one in Washington, the space.
Yeah, and others, with others.
Got it here.
Okay, so that's one thing. You could have imagined that electrification of railways was something that happened way later, and that there should be the thoughts of interoperability and the possibility of traveling internationally. Yes, we have, but we have various systems in place. And it's even the case that some countries have multiple systems in one country, like France, for example. So this is a map of Europe with the electrical systems that we use. And you see, this causes some difficulties. You have countries like France, for example, that operate with two systems in one country and even mixed areas. So this is a nightmare for interoperability. So if you want to have a night train that goes from Berlin to Madrid, for example, yeah, your train needs to have the capability to, let's say, be capable to operate in 1, 2, 3, 4 different electrical systems. That's the case. And this is just an example. There are many other stuff that is harming interoperability. Also, you need to have national certification, both for rolling stock and for trackside, in order to be admitted for legal use in the European countries. It is still the case. We have the standards, as I mentioned, and Oscar asked before, that they are somehow mandatory by law. It's not like in automotive that you should fulfill ISO 26262, but you have the possibility to get a car certified and running without having an official certificate. For railways, it's mandatory. You need to have it. Otherwise, you will not get an approval.
Sorry, to correct, so in ISO 262 is a standard and not a law. So therefore, you can do whatever you want. However, there is a law in Europe which is called the UN ECE regulation number 157, which refers to ISO 262.
Yeah.
So in order to be compliant with the law for ALKS, automated line keeping systems, you have to implement ISO 262 in Europe. In US, it's different. They don't have this EU regulation. You can bring the car first to the street, then see what happens, and safety check last. So I say in Europe, we have safety first. In America, you have safety last. Yeah, as a pedestrian,
I disagree.
as a pedestrian, I'm fine with it.
Tesla's are running in Europe, in the US, okay.
As a car driver, maybe it's more better to be in US, but as a pedestrian, surely here in Europe.
Definitely.
Sure. Yeah. First steps, however, are made in the European Rail Agency and the TSI regulations in order to foster harmonization. But as you've seen before, there are still some hurdles that might take a lot of work and money at the end to have it unified. But the trackside infrastructure up until now still remains a national certification issue. And you also don't have a European railway company that operates the European railway network. You have a German one, you have a French one, you have an Austrian one, you have a Switzerland. Other jurisdictions, such as like US or China or Japan, do not enforce the compliance to any of these standards as they are European standards, of course. But they enforce some certifications, but it's not easy to find out what actually are the hurdles and what you need to fulfill in order to get a railway vehicle or railway infrastructure admitted there. So if anybody has any information about that, we would be glad if you could share it. All right, so let's dive into some architectures that are already placed, that have been pitched, that are interesting. As I said, most of the innovation in railways comes from Europe. That's why every of these projects and every of the information that I'm going to show you is based on a European or German-led project. We have the OCORA initiative. This is something where European railway companies have connected together in order to have a specification for safe computing platforms for future rail operations. We have from the German railways the so-called Digitale Schiene Deutschland initiative that also claims to have vendor-independent, safety-enabled computing platforms with the two projects, SIL4 Data Center and SIL4 Cloud, that I'm going to talk about. And the European Union is also financing railway research projects to its Europe's rail body, and I will also give you some insights about what is currently in operation with the FP2 R2D ATO project. What are requirements for modern railway computing platforms? We want to mostly use commercial off-the-shelf hardware and software because the railway market has the challenge that the amounts of vehicles are not so big, and this, in fact, in the past led to extremely highly customized developments that were extremely expensive, and this is not sustainable anymore. We want to have multi-vendor or multi-tenant safety applications possible on these computing platforms. There shall be the possibility for mixed criticality systems operated up until SIL4. The system should be capable of evolving, so if there is a need for potential more potential power, that should be possible. And we want to gain some more independence of life cycle of components like hardware, operating system libraries, and applications. And it should also be possible to have recertifications for parts, which is up until today also something that is difficult. All right, let's dive into OCORA. This is the OCORA generic safe computing platform. You see the pitched reference architecture here. Not much to say about it. There are three options, actually four options that the OCORA initiative lines out. So you can achieve it without any operating system, so running bare metal. You can also achieve it by having an operating system running on the hardware. You can introduce a hypervisor, and there's also a fourth solution with some virtualization and orchestration. There is no concrete technology given there, so also containerization may be an option in this case to have separation. And the critical aspects like memory management are, for example, handled by the guest OS outside the control of the platform below the platform interoperability API. And it's more challenging for the safety assessment and authorization, this option, like the other ones. So, just short. So at the end, it all comes down to integrating the systems together. And up until today, mostly the railway companies tried to buy everything from suppliers. With this new architecture, some of the responsibility will at least come up until the actual operator at the end. With integrating multiple systems together if they want to reuse some computing platforms. So this is something that the railway companies need to deal with. But I guess that's what they are prepared to do, at least some of them. Let's dive into what the Digital Schiene Deutschland has developed with Sil4 Cloud and Sil4 Data Center. The Sil4 Cloud architecture is mostly driven by Thales. And we don't see any safety claims that are relying on the operating system here. So they use a commercial off-the-shelf Linux and put our safety layer on it, and everything else that is safety related is being handled by this safety layer. And they have multiple applications that are running up on the so the operating system just needs to achieve the so-called basic integrity in accordance to EN 50716, but there are no safety claims on the actual operating system. So that's maybe something that is notable here. And the application layer is divided into safe and non-safe applications to have the possibility of mixed criticality in the same hardware. Safety layer does everything like deterministic scheduling, voting, fault management, redundancy management, and hardware supervision. And a custom OS distribution with kernel and services tailored for each platform release is necessary in regards to CPU family, sport specifics, and hardware. So you can use basically everything, but it is highly customized. So Sil4 Data Center is doing a, I would say, similar approach. We also want to have commercial off-the-shelf hardware. We want to have a load OS and some kind of virtualization going on there. It's still mostly commercial off-the-shelf components that should be used, and also there's the support for multi-vendor apps in the runtime environment. So legacy applications can still be running on the virtualization. It's possible to have containerization combined as multiple possibilities, but also no safety claims made on the Linux itself. What the Europe's Rail does is they all come up with pretty much similar solutions, I would say. It's more theoretically driven here, what they show in their documents. So if anybody's interested in reading the actual documents, I guess the slides will be going to be available at the end, and we always have the references, so you can access the documents yourselves. One goal of the modular computing platform, as pitched by the ERGU initiative, is to achieve hardware independence at the interface I3. So they introduce these interface numbers, and they want to say everything up until from the virtualization should be hardware independent. That's what they want to achieve here. And they want to aggregate several functional systems of different safety integrity levels, possibly by different suppliers, on the same virtualization. So that's the mixed criticality use case, basically. which is also something that all of these projects have in common. One basic architecture that they pitch is this one here. So in this case, the interface 3 is not an interface in the sense of a programming interface, but it's the definition of needed functionalities and features within the virtualization layer from the view of the functional systems running above. If you make this a little bit more precise, you have the possibility to use containers as this virtual environment, which leads to the following fact: all functional systems must be based on the same OS. So this has the benefit that only one OS has to be maintained.
So
You have, yes.
are we assuming that it's the same OS configs? Yeah, it could be, because every time you can change a config in something like Linux, it's effectively a different story here.
Yes,
Are we trying to have a unified config set here?
I guess that's the goal that would make sense in order to have this benefit of just having to maintain one OS. So, but this is the documents are not so clear.
Precise, yeah.
What you see definitely here is that there is weak resource isolation. You have an overall integration necessary, but this gives you, of course, a benefit, and the benefit is that you might save resources. But you will have to test your performance overall for this architecture. Another possibility that the project is, of course, offering is using a hypervisor as a virtualization environment. I guess I don't have to get too much into it. Hypervisors are pretty familiar for most of you guys. Also, you can combine hypervisors and containers if you like. This is also something that these specifications are aware of. And we have provided we have provided a table that compares both containers and hypervisors with their advantages and disadvantages. So from the OS flexibility point of view, container technology doesn't necessarily give you so much flexibility than using a hypervisor, because with the hypervisor you can run any guest OS as you like. So you can also use Windows and something like that on that. For the containers, they must actually at least be the same type. For the maintenance, actually for the OS, containers give you the advantage to say you only have to maintain the host kernel and only one OS. Everything else is off limits. For the hypervisor technology, of course, you will have to have additional effort to maintain multiple guest OSs. In technical dependencies, you see that there are common OS kernel and functional systems running above. There's a dependency between the common OS kernel and the functional systems running above on the container side. And you don't have these technical dependencies if you use a hypervisor. When it comes to isolation, the hypervisor gives you the best isolation of resources. With containers, it's weaker, but of course, this has its advantages and disadvantages in regard when it comes to resource efficiency. Containers might help saving resources, whereas if you use hypervisors, you might have higher resource demands and a higher performance decrease compared to containers. And when it comes to integration and testing, Overall performance testing is necessary when you use containers. And you need to have some part or somebody who does the overall integration and qualification of the entire system at this point. For hypervisors, they don't state anything about that in the documents. But if you want to read it yourself, as I said, the links to the documents are in the slides.
You have one typo.
Yes.
In the beginning, right? The file systems rather than function systems.
Yes,
Or
you're,
flexible. So
you're right. So I'm going to fix it.
you're great.
I've seen another typo somewhere else
Yeah.
before, but I will
Yeah.
fix that as well.
Great.
Thanks for lining it up. So the documents also line out a architecture for a onboard computing platform, which is a little bit more specific. In this case, the proposed architecture is using a hypervisor for SIL4 functional systems and have a containerized solution for basic integrity functional systems in parallel. So this is the SIL4 part, and this is the basic integrity part. So this is what they propose to do for their applications. And what is actually one of the most used patterns in railways is using redundancy and diversity for Linux. So up until today, most of the systems are being used with redundancy and with diversity that are already being used with Linux today because usually it's not an issue from the energy side. It's also not an issue from the space side to have multiple computing instances available. If you think about the costs of how much a train is costing, the computing resources are also not a factor at the moment. This is why redundancy and diversity are somehow the way to go for Linux-based systems. And I have two questions for the audience with the picture that I'm showing here. Which SIL level can be achieved with a containerized solution? Anybody, any ideas?
Would say depends.
That's a good answer.
So the physical redundancy,
Yes.
well, it strictly depends on the hardware, safety certification and all this stuff, right? So
That's a good answer.
Yeah.
And is redundancy in general something that we with diversity something that we should be considering more carefully when it comes to Linux and safety applications anyway? Any comments on that?
So one of the problem with Linux is that it is not predictable, let's say. So there are some aspects that they work, but they don't work each time in the same way. So at least my understanding of redundancy in the railways, you have things like lockstep or things like this. I don't think you will going to have the same result because in the time you need to be very strict with predictability. In any moment, in any time, you need to know precisely which will be your state to see if another system will be in the same state and then detect a fault. So for this aspect, I think that would be at least tricky to achieve the same level of using Linux, at least.
Thanks for the comments. Any other comments?
Just generally up till now, where you have really high safety requirements, like so for, you generally are using not Linux, but more low level RTOS kind of operating systems on RTOS hardware up until now. It'll be interesting to see how it shakes out when you really start getting into use cases, functions with high safety requirements like SIL4, ASIL-D, and high compute requirements, right? Where you're really doing like autonomous camera-based driving, where you've got to do image processing, but you have high safety requirements, something like detecting whether the state of a traffic light or something like that, right? I think we're really there yet, but I could see it coming, and then we would have to solve the problem of how to do Linux with high safety, and I could imagine that redundancy could be the solution.
Is it not going to be expensive?
So-
Because we want consolidation, everything on one, everything. The price is the main factor most of the time.
So if it comes to trains and it comes to if it comes to the railway specific situation, so I guess an ICE train is in the millions. If you have computing resources that are, I would say, 20, let's say 50,000 euros, if you take all the redundancy in fact, maybe also 100,000. I'm not sure with the lifespan that such a train has. So we are always talking about 15, 20 years that they are staying in operation. If this is becoming a significant issue.
No, like more not the cost of the train.
In cars, definitely.
No, not the cost of the train making it, because like in the train industry also, like I don't know, like, but the weight of the train also matters a lot, because how much the payload is. So if you add diversity of everything, the other than passenger, the weight itself of the train will be start increasing itself, and then the cost of running it will also start increasing. The longer time you have, the longer time you have to do it. So like that's why the material they use, they have to be very careful. It has to be not used for a long time. It also not have to be weight. So I don't know how much you can diversify, how much in this domain.
I think an interesting element, like the thing is about the maintenance afterward, right? If you share different architectures. And I remember one guy from EMQ, I think he's from EMQ. He told me that he had a lot of issues in maintaining his home setup, because he has a Raspberry Pi and somewhere in the basement for some parts, which is like the worst case when he needs to look up something and wants to do a little bit. Then he has a standard laptop, which he uses for development, and he brings a development PC, dedicated desktop, with more performance. And he said he had long time issues in maintaining this setup, because we have ARM architectures, we have x86 architectures, we have the combination. But he said, and I don't say that's the solution, right? It's just like how he has tackled it. But he went, for example, to Nix with Nix OS, and he said now he can maintain configuration, and it basically, whenever he modifies something in the environment for his laptop, does changes to how his editor looks like, or so it's directly getting reflected to the synchronization to the different architectures, and here a level of extraction is reached. Then you would still say, well, I have a lot of similarity in the base system, but there's a lot of parts which you can control, and the uncontrollable part, which makes it much harder to argue portability, which comes into this picture. Then you can say, well, I have 3 types of architectures here which I use. Memory will behave differently, caches are different, execution is different. So you can come in an argumentation. And I mean, that's also what railways is already doing, where they come up to level 4 parts for signaling, for example, where they run Linux and Windows in parallel, And by this can say we have diversity on the operating system level, that runtime issues are so when I develop my application according to the standards. So I can have my safe application and I can put it on a QM operating system and argue diversity and see that I always will be operational on the sites and that the one error will not cause another one. And I think they still go on the 2 out of 2 and not a 1 out of 2. So they are not accepting a mistake. So they say, when I see the same computation results on both systems, which one is running on Linux, the other one is running on Windows, then I can eliminate the operating system from it. And this can also help in hardware. It's not the solution of all cases, hence like one before, but I think that's something which can be taken into account. Isaac, you don't look convinced.
Perhaps one thing from let's say avionics. If you have a, let's say, flight control system, the question is why you make redundancy. I think redundancy you make that you make the decisions more safe, and you also, let's say, avoid an impact of any hardware failures or something like that. But in avionics, normally the 2 channels must be developed for flight control for the highest level dissimilar. So you need 2 different operating systems as now expected with Linux and Windows. And you have also dissimilar developed hardware to assure that you in these 2 chains, you will not be faced the same problems. And but the biggest problem, I think, is all the time on redundancy is the voting, which channel is the proper channel. And this only works if the algorithms have an output on the same input. So you have to synchronize also your inputs to be sure that you are able at the end to compare some stuff. This is also open up a problem with the redundancy, the voting, who is right which channel. I think this is really a problem. So sometimes it's better to have no redundancy and to be sure that your channel is working properly. This you do in the aircraft up to DAL C. Normally you try to have only 1 channel. If you go to DAL AB, you try to have redundancy, and then normally you have dissimilar developed channels.
Yeah, and also I want to add like the power. The usage is also one of the main factor, not in automotive or space, but I worked like in the space one. And there you want to add redundancy, but you don't want active redundancy. You want have like, because if you are running 2 operating system, you are withdrawing power from the batteries all the time. And you want redundancy and you feel like there is a time when you feel like, okay, now I'm in a state where I cannot recover. And then you choose the other architecture or other things where it's because you cannot send an update or something like this. You just feeling, okay, I have now concluded. Now it's not in a working mode. Let's move to another one where there is no permanent failure, and then I choose to the redundant one. So even if we run 2 operating system, the power consumption is also one thing, which is also, if you can run redundant in operating system, but then it means you are withdrawing more power from the batteries.
That's an issue for space, for example, but for railways, it really isn't, because usually if you're on an electrified train, you have permanent grid connection and basically unlimited power available.
Yeah, but it's becoming also a problem now in automotive that you want to have longer battery like a drive time, and you cannot have like running multiple operating system just because you cannot complete in one thing. So like I fully agree with the railway. You might not have this because you are connected to the power, but in other industries, this redundancy of software does not come just because of the power consumption.
So it depends. If I might conclude, it depends on the system and on the operating conditions.
Yeah,
It's very important to take into account that if we assume that this system should be fairly operational, as it was mentioned for airspace, for example, and then we need to take into account that once any failure happens, then the system should provide correct results, because one more aspect that should be taken into account. Or it is fine that this system can fail, and after that start operations from very beginning if we have some kind of fault redundancy. And there is a second aspect that is very important, that each of those operation systems, they typically providing some diagnostic measures for the hardware. So that in addition to providing some votes out of the information that we get for application, we typically need to analyze information about the hardware diagnostic that will contribute to vote, so that we will have something like 2 out of 2 with diagnostic, not 2 out of 2 with diagnostic, not without diagnostic. If we're talking about already sealed or ASIL qualified hardware.
How many more slides do you have? Just like you just here.
Pretty much at the end.
3 minutes.
Perhaps one last to your previous slide, to the first point, the categorization. We are at the task 2025. We have prepared a paper together with DLR proposing WebAssembly containers to come up to DAL A, which is ASIL D or SIL 4, I would say. So I think you can reach with containers the highest level. That is also intended to have everything containerized.
If that paper is public, can you put a link to it in the chat?
Yeah, that would be great.
Yes, I will do that.
Thank you. I think others in this room would be interested in reading it.
I'm sure they will. So this brings me to the end of my presentation. Any other questions? Any other comments?
How long does it take to produce such a system? How many years?
Which system are we talking about?
Computer platform.
I guess at the moment, most of these architectures that I have been shown, I have shown you are theoretical at some point. So they are not yet in operation. If they are in operation, it's what Siemens, Thales, or these railways manufacturing supplier companies would do. I have no data how long they take for their developments. I'm not aware of how long their development cycles are, but I guess due to the nature of the lifespan that these components have, not only on the rolling stock, also on the trackside, we are always talking about at least 10 years, more, maybe more than 10 years, 15 years, 20 years. It's the development time was not really a significant factor. Anything else? Then thank you very much for your